All right. Hey, everybody. How's it going? I'm SPITLER. I work at Bitfusion. I'm the lead data scientist there. And kind of what I wanted to talk about was deep learning frameworks which utilize Spark and GPUs. And also, this is kind of the abstract of the talk. And this is kind of the agenda, right? So I'm going to talk about the current deep learning landscape. I'll do a small case study. We'll talk about, from the case study, some practical considerations that you might have when you're doing deep learning and such things as like your data size, your hardware configurations, stuff like that. And then future work that we kind of want to look at as far as like new papers that have come out recently and things that are on the horizon. And also kind of an overview of what Bitfusion provides in this space. So before I start, like, quick show of hands, who's written their own deep learning model? Okay. What did you use?
Doing that LinkedIn.
What framework did you use?
All kinds of things. Jobs, better jobs, ads, news articles.
No, like what deep learning framework?
TensorFlow.
Okay, cool. And what about, I think there was one person over here? You use H2O. Okay. So TensorFlow and H2O. So let's kind of like talk about the landscape in general. So there's been a ton of frameworks and kind of more boutique frameworks that have popped up over the last, 3 years, 4 years. So some of the base frameworks that you kind of see are TensorFlow, Caffe2, PyTorch, MXNet, Caffe, Torch, and Theano. Some more boutique frameworks are things like TensorFlow on Spark and Caffe on Spark. You can use a bunch of different data backends. Here are some of the ones that I've used personally. Just regular file system, EFS, Spark, Hadoop. And then also where you're going to deploy your models, right? It could be AWS, Google Cloud, IBM's Cloud, SoftLayer. There's a bunch of different options as well as your own hardware. So this is kind of an overview of why Spark. Why would you use Spark for deep learning? So you can access many data sources, environments, applications. There's real-time data, resilient distributed data sets, HDFS integration, which is pretty big, especially since I don't know if you guys went to the TensorFlow and Spark talk, but he talked about how TensorFlow has native HDFS integration with its data runners and queue runners. So that's pretty powerful. And then data scientist workflow in general and how it can integrate really nicely to how data scientists are kind of already doing things today. So we're going to kind of talk about not only some of the deep learning integrated, so now we're going to go into the more specific deep learning integrated frameworks, right, with Spark. So Caffe on Spark and TensorFlow on Spark are probably two of the most popular ones. And this is kind of an overview of how it works. Of particular interest for this slide, and I'll get a lot more into this later on, is the fact that it uses RDMA over gRPC. That's going to play a pretty big role, especially when you go to distributed jobs. Another one is SkyMind AI in their Deep Learning 4J framework. So I think what's interesting about this one is their Canova offering, which kind of gives an interesting way to do vectorization if you're doing a lot of text-based deep learning things. So SystemML is another one. This was a little less mature, but it has some interesting functionality. It'll actually automatically optimize, to some degree, your network and your runtime hyperparameters based off of data and cluster characteristics that you provide for it at runtime. So this one's pretty interesting. BigDL, which is IBM's or Intel's offering. It's kind of an overview of this. And then, so now we're kind of getting into the case study that I did to kind of illustrate what you need to think about when you're trying to do this practically, right? So I wrote this case study as if you're just getting into deep learning. You're going to do the first thing, you're probably going to use the most popular frameworks, and you're probably going to use the most popular cloud compute offering, right? So I'm going to kind of show you as you move through your life cycle of those things. And once you get to a certain point of your life cycle, you need to start thinking about hardware and what your cloud provider is providing you for your deep learning framework. So kind of an overview of Google TensorFlow. It's by far the most popular deep learning framework out there right now. I don't really consider Keras a framework. It's more of a abstracted front end, and it can have multiple backends, right? So it can have TensorFlow, Theano, and they just released CNTK support. So this top right graph kind of gives you a good understanding of what they've been working on, right? So this was at the TensorFlow Dev Summit. They kind of talked about this stuff. The TensorFlow layers was kind of an intermediary or an alternative to Keras as a higher level abstraction for your neural networks. And this is just kind of an overview of how it works, right? So again, to show you why I use TensorFlow, it's by far the most popular as far as machine learning frameworks, GitHub stars, and also Stack Overflow questions, right? So you can really see how popular it is relative to the other frameworks. And then also, what's really interesting is it's actually growing a lot in academic popularity. So this kind of gives you an idea that TensorFlow is not going anywhere anytime soon, right? The research community is starting to back it a lot more than they used to. It used to be mostly cafe. So if you're looking for a good place to start, TensorFlow is the way to go. So let's move on to the quick case study, right? So this is actually what we're going to be testing. So this is the network that I ran. So I'm just using the CFAR10 data set. The architecture is shown to the right, but basically I have kind of two modules, a 2-convolution module and a 4-convolution module. And in the 2-convolution module, I have a 3x3 convolution followed by a 3x3 convolution, and then a max pooling layer, which has a stride of 2 and a kernel of a 2x2. And then the 4x4 is just the same thing except 3x3 convolutions before the pooling layer. And then it's followed by a couple of fully connected layers, and then an output layer, which has a depth of 10, which corresponds to the data set, right? CFAR10. So CFAR10 is 10 classes of images. It's basically, I think it's dog, cat, car, truck, bird, and a few other ones. So basically, we're just creating a basic image recognition network right here. So for the benchmarking, the thing that I really want us to note, images per second is popular and it's reported often. What I wanted to show was time to 85% accuracy, because this can actually get a little bit tricky, because in a lot of the marketing materials that I've seen, images per second can get beefed up really high if you just beef up the batch size. But from a practical standpoint, what you actually care about is how fast you get to a viable solution, right? So that's why I'm going to talk a lot about the 85% accuracy. And then at the end, I'm going to talk about Facebook's paper that they just published that uses Caffe2 and Glue that might change these numbers in the future. Another thing that was really important is all the models are run on P2 AWS instances. The hardware is completely homogeneous. I didn't do anything special for a framework. I just basically was taking the consideration that you're picking this up, you're going to take it, and you're going to go. So finally, the model configurations that I have are single server using CPUs, single server using a single GPU, single server using multiple GPUs, multi-server distributed TensorFlow, and multi-server TensorFlow and Spark. So let's kind of get into it. So for the single server, the CPU and the GPU performance is as follows. Right, so the CPU was processing about 130 images per second, and it took around, 16,500 seconds to get to 85% accuracy. And when you compare that to GPUs, you get about 1420 images processed per second, and your time to accuracy is 1545 seconds. So basically, it was a speed up of about 10x when you move from CPUs to GPUs on TensorFlow. And what you see there is the time it took me to get to 85% accuracy. The reason it's kind of a stepwise graph or a piecewise graph is I only updated the accuracy every 5 epochs. So kind of the headaches that you have to deal with when you're traditionally moving from CPU to GPU is configuring CUDA drivers, configuring a lot of the frameworks to be compatible with GPUs usually takes more time than you would suspect as far as the troubleshooting and stuff like that. So the next one is single server multi-GPU. So for this one, I use 3 GPUs. I still use the same GPU card in the P2 suite, but I had to go to the 8 extra large to get multiple GPUs on one machine. You can see the images per second spiked up a good bit to 3,200, and it took about 735 seconds for me to get to an 85% accuracy model. So I'm going to kind of note some of the code changes that you kind of have to work through to get these things to work. The main thing for GPUs is you have to place your code on devices, right? So you hear a lot about model parallelism and data parallelism. It should be noted for all of this, I use data parallelism, not model parallelism. And the main reason for that, and then I'll kind of get into the practical consideration of deep learning frameworks and models later, but my model just wasn't big enough, right? It's not big enough for me to see any speed up, really, if I did model parallelism. So data parallelism is the way to go, and basically how that works is you place your model on each GPU, you feed it a subset of the data, you compute the gradient, and then you average the gradient across all of them, and then you repropagate that to the GPUs, or the model on each GPU. And that's exactly how model parallelism works in multi-GPU as well as distributed frameworks. So the TF device is basically TensorFlow's ability for you to place things on GPU 1 versus GPU 0 versus GPU 2. So then we get into distributed TensorFlow. So this is kind of where things get interesting. For what I was working on, which was the P2 extra large, I actually got a significant slowdown from the multiple GPU when I went to a 3-server setting, right? So this one uses 1 parameter server and 3 worker servers. So 3 workers should correspond to the 3 GPUs I used previously. And it actually reflects more closely to the single GPU setting than the 3 GPU setting. So I'll deep dive into this a little bit more later as to why you would see this. But some of the code changes that you kind of have to take note of is your session. So usually you have some piece of code called tf.session. That has to become tf.monitored session. And then there's some interesting gymnastics that you have to go through to balance batch size and learning rate to optimize your throughput. And then the last one is TensorFlow and Spark. So the performance is better than the vanilla distributed TensorFlow, but still more similar to the single GPU than the multi-GPU one that I showed. And then this is kind of noted in the other talk, but some of the key things that you kind of have to change in the code are, tf.train.server, tf-node start cluster server, and then there's a few extra TensorFlow and Spark specific code changes, but they did a really, really good job of making it very easy to change your code to run. So here's kind of, I was giving you numbers before. Here they are all stacked right beside each other. The bottom one, I removed the single CPU just because it was much more time and you couldn't really see how they compared to each other. So obviously you can see the multi-GPU worked the best for this setting. So usually when you're looking at distributed stuff, you see close to linear scaling. So why didn't I see that, right? So that's the question I get most often when I talk about this stuff. And the main reason is your hardware really, really, really matters when you're going to a distributed setting with any of the frameworks, right? And the reason behind that is you're making a ton of updates, right? So if you think of the deep learning models, the thing that's really interesting about them is you have, tons, millions of parameters. And when you're doing your updates, all of the workers have to communicate to that parameter server, and the parameter server has to recommunicate to the workers. So your network matters a lot when you go to this setting. So the ways that you can kind of mitigate that is increasing your batch size significantly such that you saturate the GPUs as much as possible and decrease the amount of network communications that occur. Another way that you can do it is there's kind of three main communication protocols that you deal with when you're dealing with deep learning frameworks. There's gRPC, RDMA, RDMA over InfiniBand is a particular interest, and then there's MPI as well. So what we kind of show, or what we kind of see, is that RDMA over InfiniBand was about 2 times faster for 2 nodes, and for 4 nodes, you got about 10 times speed up as far as those network communications were occurring versus gRPC. And so distributed TensorFlow's native communication is gRPC. TensorFlow and Spark gives you that free RDMA over InfiniBand communication out of the box because they basically fork the repo and add that functionality in when they provide their own version. So this is kind of a little bit more technical, but this kind of shows you what you're looking at when you're grading the different communication protocols, right? gRPC versus RDMA versus MPI. The basic takeaway that we found from this was InfiniBand, or RDMA over InfiniBand was by far the fastest that we saw. So some more practical considerations to kind of think about when you're writing your models. The size of the input data, that batch size, is really, really important. The number of so this is kind of like illustrating why you would maybe want to use a distributed file system over something more native. And then also, size of the model is very important. When you get to a certain size of model, you might have to go to model parallelism. So that's where you place pieces of your architecture, kind of that architecture that I showed before, on different GPUs. And so this one will compute up to this point, it'll communicate its results, and then the next GPU will communicate the rest of those results. So the main takeaway is GPUs are almost always better. That's been the case for basically since AlexNet came on the scene. Your hardware and network setup matters a lot, right? Especially when you're going to the distributed settings. It's really hard for you to get up and running if you're using commodity cloud offerings. you actually really need to optimize your network and your hardware to run as efficiently as possible. The next thing is saturating GPUs locally should always be the priority before going to a distributed setting. If your data is already built on Spark, TensorFlow and Spark provides an easy way to integrate with your current data stack. And also, they already come with an offering of RDMA over InfiniBand, which is really important for those network communication speedups. So some of the future things to look at. So these are things on the horizon that I'm looking at, but I didn't have time to add to this paper or this presentation, are Cafe 2, and specifically a paper that Facebook published recently, which was called Accurate Large Mini-Batch SGD Training ImageNet in 1 hour. And so what they use is they have their own new communication primitive that's based off MPI called Glue as their backend. So it's really interesting to see how that might cause speedups versus regular MPI and what Cafe 2 in a distributed setting might look like versus distributed TensorFlow. As well as TensorFlow actually has an MPI integration that they just pretty recently released in their contrib library. So that'd be another interesting thing to look at to see how MPI versus gRPC versus RDMA over InfiniBand and how that kind of works out. And then, so Bitfusion does a lot of these studies to kind of know what the best in class is for particular models. So for more studies and scaling of deep learning workloads, you can go to our website to learn more. And to kind of give you an idea of what Bitfusion is in particular, is it's kind of two things. The first one is it's a GPU virtualization software. So what I mean by that is if you have your 5 servers with 2 GPUs each, we allow any one server to behave as if all 10 of those GPUs were native to that one computer. So when you're thinking about practically, when you're running deep learning frameworks, when you're going from a small model to a larger model, when you're trying to eke out that performance, usually what you end up doing is you write the single GPU version, which is pretty native. There's tons of examples on that. Then you'll go into a multi-GPU model, right? So you'll rewrite the code to run as if it's a multi-GPU model. There's a lot of examples on that. And then when you're feeling like making that next leap, you usually rewrite your code again to be in a distributed manner. What we allow you to do is skip that distributed step, right? All you have to do is have a multi-GPU model, and you can run your multi-GPU model across however many GPUs you want. And again, there's tons of examples for multi-GPU. Distributed code is pretty sparse on the internet or when you're getting started. So that's kind of the first offering, is that virtualization layer. And then we also provide a GPU management layer on top of that, which, and you can see on the far left, it's kind of showing all the GPUs available for a computer, which ones are allocated versus not allocated. We also provide multiple Docker containers with all of the most popular deep learning frameworks, TensorFlow and MXNet. We're working on PyTorch and Cafe 2 right now. And it also lets you launch interactive workspaces. So if you're comfortable using Jupyter, then you can go through there. And there's also a CLI offering as well. So that's kind of what Bitfusion is. And we also, to kind of tie it back to the talk, what we do is we actually optimize the communication protocol based off your hardware, right? So if you do have InfiniBand, we'll use RDMA over InfiniBand. And if you don't, we'll use gRPC, or we might use MPI depending on your workload. So that's kind of an overview of Bitfusion, and that's it. Any questions?
First question is, in terms of running this on a Yarn, I know a lot of this stuff is done with CUDA
Yeah, so the question is, do we provide support for running a lot of the CUDA libraries through Yarn or getting it configured, right?
Yeah.
Okay, so if Bitfusion started as you guys might have known the company from the AWS offerings that we had, right? So we had a lot of AMIs that you could use for deep learning frameworks. And in that sense, depending on requests or popularity, we can provide a Docker container for you to kind of set all that stuff up. Or you can create your own and bring it to the platform. But as far as us doing that specifically, no.
Does the Bitfusion allow you to use disparate generations of cards, like a bunch of K80s with like P100s?
Yeah, so the question was, can you use K80s with P100s integrated together, right? So the answer to that question is yes. You can use whatever you want as far as an offering, but again, you have to think of that as it will definitely throttle your network, right? So when you're thinking about multi-GPU and distributed models, distributed maybe less so because it can be run asynchronously, right? But for multi-GPU models, usually what happens is you'll run here, here, here. They'll all wait till they get a result, and then they'll average those results, right? So there are ways to do it. Distributed definitely gives you the asynchronous ability, but as far as, I forgot to mention, Bitfusion runs anywhere, right? So your own hardware runs on AWS, GCP. Wherever you want to run it, it can run. And yes, it can run on old GPUs, new GPUs, a hybrid of GPUs. And we're actually looking at doing other processing units and bringing that on as well. And you had a question?
Yeah, so the example that you showed with the Spark, is it a Spark cluster or Spark running on Yarn?
So it was, if you go to TensorFlow and Spark's GitHub repo, they actually have a deployment on EC2, and that's kind of what I used. Any other questions? All right, guys. Well, I'm going to be around for a while, so just